For this lesson, we're going to be finding the area between two curves. So here's our first problem. You might want to pause the podcast to go ahead and write it down. I'm going to go fast from this point on. Okay, so I want us to imagine that there's a rectangle here, and to find the area under the curves, we're just going to do what we did before, we're going to add up the rectangles using integration. Okay, we're going to pretend this rectangle is very, very thin, so its thickness or its base is going to be dx, and its height is what's kind of tricky. If you notice, the height is just the gap between the top minus the bottom, so I can actually just do, in this case, the height will be the blue graph minus the green graph, f minus g. Okay, so if we take a look at one rectangle, the height of that rectangle is f minus g. The base of that rectangle is dx. Okay, so this right here is the height. This right here is the base. That's just one rectangle. To add up all the rectangles, we're going to use an integral. Okay, there's a couple other pieces that are still missing. One of the things I need to find is I also need to find the intersection. Two choices. You can graph them and have your calculator find the intersection, or you can set the equations equal to one another. That's another way to find the intersection. I'm going to move everything over to the right side. So I have x squared plus x minus 6, and you can quickly and easily factor this and see that your intersections occur at -3 something and 2 something. Okay? But it doesn't really matter because we're just concerned with the limits, so those are going to be our bounds. So the final integral to find the area between the two curves is going to be the integral from -3 to 2, f of x, which is 5 minus x squared, minus g of x, which is x minus 1 dx. Okay, and I'm assuming we can find the integral for that. The next example is the same idea, nothing really different, just extra practice. So again, I want you to imagine that there's a rectangle here that's very thin. We just got to find the height. The height again is top minus bottom. So the top function is f, the bottom function is g. Okay. So our integral again, I'm going to integrate f minus g, that's the height. Give it a little bit of a base, it's dx. Add up all the little rectangles all along this region. That's the integral. And now the question is, how do I find the bounds? Well, in this case, I would just use the graphing calculator, figure out what the bounds are, and plug it in. So from A to B, whatever those turn out to be, they are probably going to be decimals. Third problem is we're integrating sine and cosine. So sine, remember, begins at 0, cosine begins at 1, and we're just going to focus in this quadrant. Now, we have to get the intersection first, so it turns out the first intersection here is pi over 4, and based on your unit circle knowledge, you can get the other ones. This one is at 5 pi over 4, and then this one is going to be at -3 pi over 4. So these are the intersections of sine, cosine. Well, why are we going through this problem if it's similar? Because I want you to notice, in this region here, that the top and the bottom is very specific. So for that region, the top, it turns out, is cosine. And then the bottom is sine. Give it a little bit of a base, and then integrate. And it's only valid from -3 pi over 4 to pi over 4. Okay. If we look at the next region here, I want you to notice that it has switched. So this case, the top function is sine, the bottom function is cosine. Give it a base, dx, and then we're integrating that from pi over 4 to 5 pi over 4. Okay. The last problem actually just turns things around. So here's the function. Again, pause it if you need to write it down and copy it down. Okay, the idea here is that we have functions that are in terms of y, so x in terms of y. So these are sideways. This one's a sideways parabola. This one is a sideways quartic graph. You could, if you want, integrate from top to bottom, but notice that it gets a little weird because there's a strange switch in between. And in fact, the top and the bottom are the same graph. And you would have to solve for y. So that's a little bit strange. So we want to see, is there another option that we can use? Well, it turns out there is. So instead of doing top minus bottom, we can actually change our orientation and build the rectangles going this way. Okay, so we're going to build the rectangles going this way. In this case, to get it, it's going to be right minus left. Okay, so the height of the rectangle is going to be the right side minus the left side. So in this case, the rightmost function is the green one, which is negative y squared plus 2. The leftmost function is the blue one, which is y to the 4th. So that's the height of the rectangle. Notice the base now is in this direction, so it's now dy. So the rectangles are kind of going in this direction. Here's a little rectangle to represent that. So it's going to be dy, and then we're going to integrate. Because we are integrating in dy, that means I need y limits. So if you look at these or find them algebraically, that right there is at -1, -1. That one is at 1, 1. Okay. The limits I'm going to use have to be the y limits. Okay, and like the x limits, I'm going to start with the lower number on the bottom, the higher number on top. So I'm basically integrating this region from the rectangle down here all the way up to the rectangle at the top. Okay. A couple instructions on the homework. Number 1, just do 2 by hand. Okay. This is section 7.1. Okay, do 2 by hand. The rest you can do calculator. Okay, in fact, the first few you only have to set it up.